So, it is streamy time again. So let us see whether this is working. And then we can hopefully get started. Yes. That looks promising. We have a signal. Now see if I can hear myself. Is working. We can hopefully get started. Yes. All right. So, here we are, born to be kings. We're the princes of the universe. No, wait, wrong movie. Sorry. Hello everyone. We are still combining our parser and bytecode interpreter from the previous chapters into an actual programming language. So last time we wrote a pretty little test script, and what do you know, we actually managed to make most of it work. So we can declare multiple variables, all have to be ints, but I gave a few hints on how one would handle different data types. We can parse assignment statements and other expressions, and we can return a return value that will actually get printed if you run the program. Wow. Let's just do that, run the program. See. Yep, we're returning 0 plus 68. Oh, we should probably run this with a different value just to see that the addition actually works. Nice. Yeah, and we're actually logging everything that happens. So we see we're logging the script, we're logging all the tokens we split our script text up into for easier parsing, and we even log the tree into which we build our program. So you see here, it gives you a variable, well, a parameter, and here it has the two variable declarations. Here it has the assignment statement operator call equals that assigns to x this entire expression, and that expression is x plus 68, so a variable plus a literal. All of that works, and the return statement is currently parsed as a function call. So we're in pretty good shape, actually. There's two things we want to do today. First, we're going to handle parameters by simply so that we can actually pass in a value, and that will then be used. And the second thing we will do is add loops, which will probably take most of our time. So, how does one do that? Well, here's the thing. If you look at our generated code, let's do that for a spell. Run this in the debugger. Breakpoint is still there. Beautiful. So we're stopped in the debugger, and we have our array of instructions here that we built. And you see we have... Wait, do I have... No, I don't have Affinity Designer on this machine. So I guess I'll just dryly describe this instead of showing you a picture. Well, we handle variables using the load int, base pointer relative, and store int, base pointer relative instructions. That in turn takes an index, so the variable x, which is the second variable, has the index 1. If you look at the start, the y that we never use, that is the one that takes the index 0. And I guess I'll just type at the end of something. So our return value gets returned using store int base pointer relative -3. And you might remember, how does that happen? Well, when we start running this function, we first reserve space for the return value on the stack. Then we reserve space for any parameters. Well, there could be a parameter 2. We don't have one right now. Then once the parameters is done, we push the old base pointer, so we can restore it after the function or when the function returns. And then here is where we set the new base pointer, and then we have our variables. That's basically how our stack looks. And so when we address y, the index is base pointer +0. When we want x, the index is base pointer +1. And when we want the result, it's base pointer -1, -2, -3. So from there on, it seems very easy to find out how to get a parameter. And that is, you just say base pointer -1 minus parameter count, or parameter index. Well, actually, it's not even parameter index, it's one based number of the parameter, I guess. So for parameter at index 0, if you wanted to, you do -2. So now, how does this work with multiple parameters? Well, in practice, it's your personal choice. But in most programming languages, what is done is the parameters are pushed in reverse order. So that means you push parameter 2 first, and then you push parameter 1. Let's look at what our program does. So we have our run function that takes arguments. What does that do currently? It just appends arguments begin and arguments end. So that means it actually pushes them in the correct order. That, of course, means you need to know how many arguments does this function take, which in our case is 2. And then you add the index of the parameter you really want. So yeah, so that makes total sense. So why would you push them in reverse order? Well, for example, on Intel, there are 2 difference to our bytecode VM. One difference is that the result is usually not pushed at the stack on the stack before the parameters, but rather it is written into a register somewhere. So into a quote-unquote variable built into the CPU, but there are, like 10 or whatever, 20 maybe such variables built into the CPU, and some bigger data types cannot be written into a register, because registers are just like a bunch of ints of different sizes. So unless your data structure is very small, it won't fit into a register. So once that is removed, so if we ignore that, the nice thing about, let's just change this for a spell, about this layout is that if a function is passed more parameters than it actually knows to handle, that's fine, it will just ignore them. Because it will go and say, okay, my first parameter is at base pointer -2, and my second parameter will be at base pointer -3, -4, whatever. But if there's an extra parameter, it'll just be above that. And since the caller sets up the parameter and cleans them up from the stack, so that's the call instruction in our case, or the run function up here. Like if you see, what we do is we insert all the arguments here, and here at the end we pop all the arguments off the stack again. So if we passed too many arguments here, that function would not have a problem with it. So what's the advantage of that? What's that good for, being able to pass more arguments if they're being ignored? Well, think about it as a developer who has to ship a program over time. What you can do is you can have a function where you, for example, remove arguments that you just ignore from now on. And as long as they're the last arguments, now any old code that was compiled to pass you 5 arguments, once you remove the last argument and only pass 4 arguments, will still work. Because, it pushes 5 arguments, it does some unneeded work, but your function can just accept them. Also, you can do it in the reverse. If your function happens to be structured in a way that lets you pass it, that lets you know, for example, if it has here, if one of the, well, it's a little misleading to use this function, I think, but like, if this function here had a bunch of booleans at the start, or had like a number parameter on the start, a bit field, a bunch of flags, then, if you remember bit fields, you have 32 bits, and each one is a boolean, for instance. And then you often have, like, I'm only using 4 bits, but I have an int, I have a uint8, for example, so a byte, that contains 8 bits at minimum. So I have 4 bits that I'm not using, that are usually 0. So what you can do is, you can set the 5th bit to simply mean it takes that extra parameter. And then, you used to have a function void foo bit field a b, and now you update it to take ABC, and let's make C uppercase just to make sure that you see that that's the new stuff. And now if the bit field doesn't have the flag set, you just only look for A and B. You never access C. And therefore you don't get, you don't get garbage data. But like to do something equivalent to the old calls, where this extra bit isn't set, all you would do, for instance, if C was a pointer, you would just pass null instead. And then all the code that has to be compatible with the old stuff will just never access the null either. Doesn't hurt anyone. But if you then set the bit, that null or whatever gets used. So it's basically passing your parameters in reverse means your code, when used, for example, as part of a binary API, like an operating system or just a library that is used by others, so is used by other applications and might be updated independently of the application without recompiling the application. Which, you want, for example, for an operating system. You want old applications to just run on the next version of your operating system, even if you add features, even if you add parameters. And so, in that case, it would actually pay off to push your parameters in reverse. But since we're already screwed, since to find our return value, we need to exactly know how many parameters we take, that's not a problem. So now you might be asking, why aren't we reversing the order here? Why are we pushing the result first and then the arguments? Why don't we push the arguments first, backwards, so we can ignore any extra arguments, and then push the result? Well, if you remember, usually on our stack, when we do, for example, a mathematical operation, we pass the left-hand side argument, we push that, we push the right-hand side argument, and then we trigger the add instruction. And the add instruction takes the left-hand side and right-hand side of the stack, and then pushes the result of the addition. We do the same with anything else, with function calls, whatever. So what we really want, and if we pass a function as the left-hand side, what we want is at the point that the entire function is executed, we want it to be replaced by its result. So if we pass parameter 1, let's say it this way, parameter 2, parameter 1, and then the result, we need to actually remove all these things off the stack. But the problem is then the result goes away. We cannot set the result. So to implement a function that returns a value, we either would have to leave all of this on the stack, which would mean the caller would call us, and then the caller would be responsible for remembering the result somehow, and it can't really use the stack, and then removing the two arguments so that only the result of the function remains on the stack after the function has been called, because that's how the plus operator or whatever, or the function that we pass the result of one function to, expects its arguments. It just expects its arguments. It can't deal with 5 parameters being before that on the stack. Imagine we had 2 functions that take arguments. Then after they have been called, the stack would look something like this. But the plus operator expects this. And that's kind of difficult to get. You'd need extra storage for each of these parameters. Or what you need to do is you'd have to reserve space for result 1 and result 2 before you call a function. So in the location we would pass the result now, and then you pass parameter 1 result. I guess that's parameter 1a and 1b, and result a and result b. That would be result a2 and b2. This is getting complex. So, this function would get called first. You would evaluate that. Then you would write result b into result b2, copy the result value, which again takes time. Then you can take these 2 things off the stack. Then you do the same here. You'd call the function. It fills out result A. You copy result A to result A2, and then delete those 2. And then you finally have something where you can trigger your add instruction. So that's kind of a roundabout way of doing it. So that's why you kind of want the result first. There would be another way to solve this. You could for example, pass the result, not pass the result as the first argument, which, is what we're effectively doing here. If you look at this, if we're pushing the first argument and the second argument in reverse order, then the result would kind of be the 0th argument. So what you can do is, instead of pushing the result here, push a pointer to the result. And so you have a result here at, like index 16. So at index 20 is parameter 3, 24 is parameter 2, 28 and at index 32 would be the result A, and result A would just contain 16. And that way you do not need to know how many arguments you are passed, but instead all you need to know is the result is at the index specified in 0. So you grab the 16, which the caller filled out, and when your function returns, you can get rid of the 16, and the caller can get rid of all the arguments, but the result at address 16 still stays in the place where we need it to be used for the next expression. So that would be one way to work around it. Again, that's something that, your real Intel CPU often also does. For example, if it passes a data structure to a function, or rather gets a data structure returned from a function that is too large for a register, usually you just pass the function, like on the binary level. For the result, the function just gets passed on the stack the address where to store the return value. Nice warm tea. All right. So now I've held a long speech, and really all I wanted to say is we can make it so we can compile parameters. And we do this by going into our function. And so we need to do several things here. First, we need to keep a list of all the parameters. So we have this m parameters in the function. So we need to pass that on to our generate code for statements. So instead of num arguments, let's actually pass m parameters. I think that's just a vector of parameter names. Again, parameters size. Wait, no, that's just parameters because it's the same function. It's curve func m parameters, yes. Sorry about that. All right. So now, why are you unhappy? Did I pick the wrong type? Oh, it's actually a vector parameter definition, name, type. Okay, yeah, that's fine. That's actually more information than we could have hoped for. So, and it's actually a good idea. All right. So now, whenever we encounter... Actually, you know what? We should convert this first. Okay, num arguments isn't used anymore, makes sense. So we say map. Actually, why am I writing standard here? I've made it so we have a using statement here. Okay, so let's say a map string let's just call it parameter. And now for auto. Curve parameter definition in curve func parameters. Oops. And now I just say parameters. Because this parameter definition is really a parser level thing. And here we actually need a code generation level bit of information. So parameters equals parameter. And now we need to define what this data structure should contain. And the important things that it should contain is first the number of each parameter, because remember, our hash map is indexed by the names. It does not remember in which order the items were put in. So param index equals 0. Param index, since all our parameters are ints, we don't really need to care about the type, but you would probably, when you implement this with multiple types, add the parameter structure so it does that. It remembers the type, and basically you'd have to use the previous parameter size to calculate where the next one appears. So you would probably, instead of just index plus plus, you would have index plus equals size of the current parameter after you've taken the current offset, so that it skips the space needed on the stack. So parameter, what did we have? Size t index. Do we actually need anything but the index? Well, let's keep the name redundantly. That might help us in error reporting. So cur param def dot name. So now we have this parameters struct. And whoops. All right. Paste that here. That's already it. Okay. Yeah, so we could have just made this a map to size t, I guess. All right. So now up here where we parse the variable name, what we should do is here in the case where it ends, we could do it differently. I guess let's just do this error message twice. No. If it's not, then push that back and break. And now we do an equivalent case where we do auto found param. So the order here is really not that important. You could, in your parser or in your compiler, actually check that you do not allow declaring a variable with the same name as a parameter. Or the way we do it here is, if you declare a variable with the same as a parameter, it hides the parameter, so makes it inaccessible. So parameters find cur statement name. Oh right, and I didn't update the type yet. It still thinks it's a vector. Map parameter. Parumpapum. Rumpapum-pum. Rumpapum-pum. Okay, here. Find cur statement name. And now we say if found param not, whoops, params, parameters end, then push back, and now here. Remember, this is just the index of the parameter. So we need to see, we have one space reserved for the back pointer, base pointer, sorry, and then the number of parameters, and then we add found param index to it. And this should be all we need to reference parameters in our code. So let's update our script a little bit and say we initialize x to iterations. So that should be 3. And then we add 63 to it, and let's see if the return value is what we expect. Oh, right. Map, that was why it wasn't happy. I forgot the key type. Oh, and here it has to be not just index, but second.mindex, because the iterator contains a pair. And that needs to be typecast to int16t again. All obvious typos. Alright, good. Okay, that doesn't quite look right. We got 63 returned. So we have signed into iterations. We have y, which is initialized to 42, and we have x, which is initialized to iterations. So at the parse tree level, it all looks right. So let's see what happens at the code generation level. All right. Compiled code. It initializes that variable to 0, x, so that makes sense. Then it is load int so it already uses x. So the iterations part actually didn't work. It didn't generate the initialization code. Huh. That might be a deeper bug in our code somewhere. We shall see. So first let's have a peek code for the non-literal variable statements. And that says if the cur statement is a variable declaration, if its type is int32, then oh, we never implemented this. Right. That's why it doesn't work. Wait. If it's not statement literal, is I think what we need in that case. And there we need to generate basically the same code as for the assignment statement. So let's take this and copy it here. Okay, and let's say found variable current statement parameter 0 name. So it finds the variable to assign to. Generate code for statement first parameter with all that stuff, and then that would push it on the stack, and then here push back store in base pointer relative for the found variable. Yeah, that should actually be all we need to do. And we don't need the initial value. So if it's not a variable that doesn't have an assignment statement, and if it's not, wait a second, what is this? I'm not understanding my own data structure anymore. So if it's an int32 and it has a parameter zero, then the parameter 0 is the initial value. So at the least, wait, we need the name of the current statement because it's a variable. Yeah, okay, I've copied that wrong. Or rather, I didn't fix it yet, so that makes sense. Again here. So the name of the current statement is the name of the variable we're declaring here. So here we find the variable. This should really never happen. This is kind of an internal error. But, you know, be paranoid. If you see, you know, by adding these errors here, you catch the issue early. And then you just see a clear error message and you can set a breakpoint. I recommend, you know, create some sort of internal error class for these cases so you see them. And now generate code for statement. So that needs to be the value that gets assigned, which would be the initial value parsed, not parameter 1. Okay. And that gets stored in that variable. So that should now lead to what we want. So let's stop and rerun that. And now look at our bytecode. our compiled code. Load int base pointer relative -2. Right, -3 is the result. So that loads the argument, and that stores it in 1, which is x. So that's the initial value. These two lines is the initial value of x. And then here we again push x on the stack. We push 63 on the stack and add it. So if we just let this run, yeah, we actually get 66, which is 63 plus x. And since we run this program passing 3 as the iterations, you see that here, you might not remember that, but we're passing arguments into the round function here, and we're passing 3. So now we've passed arguments. So now we need a nice little loop. So first let's extend our script. So let's say we want to say, let's call this variable x, initialize it to 0. Then call this variable count. No, actually we don't need the second variable anymore. So now we say while x less than iterations, x equals x plus 1. So that's a, you could do this easier. You could just say x equals x plus iterations, but we want to test our parser here. I guess what we could do is we could add a print num x function. I think that might be a good thing to do. So let's first add that function, which should be comparatively quick. So here we have an operator call. Here we have a function call. Currently we test for return. So we just make a second copy of this. Print num. Function print num expects a single parameter. And now we go generate code for that single parameter. Okay, and that's for the return value. We don't really need that. And for the return instruction. So we don't need either of these. Just need, I think we already have a print int instruction. So let's see what this actually does. Just in case it's special, it just pops the number of the stack, says number printed, and advances the instruction counter. Okay, so that does exactly the minimal thing we would have expected it to. So this is really all we need. Generate a statement that pushes the number we were given. In our case, that will load x and print it. All right. We could probably do a quick test of that. Let's just wait. Let's save this. And the hope. Well, okay. let's say x equals x plus 66. Let's get rid of the loop. And let's do here iterations again. And let's just run this. And let's see. Yeah, it looks good. It says number printed 69. So our function gets called, and the result is 69, of course, as well. So let's undo these changes again. So now we have a loop that iterates 3 times in our case, but that's controlled by whatever we pass in. So, first thing, we need a less than operator for the comparison. Okay. So let's see, function call, operator call. Basically, less than operator should be the same as the plus operator, except comp int less than. We even have the instruction already. Thank goodness. Yeah, I mean, we had a loop before, so of course we would have had that. Okay, yeah, it just generates. We can. Well, yeah, let's leave it like this. We could probably merge this code to have less duplication. Less, just. Let's do it. Plus or. Whoops. Or less than. And then. What are these? Opcode is what it's called. Okay. Opcode up equals add int. We can probably leave it like this. If curse statement name less than up equals comp int lt for less than. All right. But then the rest of the code generation for an operator is always the same. What you could actually do instead of this here is you could build a little table like a hash map or whatever that has the operator token as the key, and the value is the opcode. And so you just say, look this up. If it finds one, grab the opcode out of it and use it here. If it doesn't find one, then it's obviously not an operator that's generic. So check the special cases like this one. But anyway, right, we can probably make this a reference just so we avoid unnecessary copying. All right, so now we have a less than operator. And now we need to implement a while loop. Okay, so first, does the parser know how to handle while? And I think that will be our first issue. Let's look in the structure. Parse function. Expect statement, I guess. It expects either a variable declaration or an expression. Alright, so optional statement parser expect loop statement. Okay. It doesn't let me go reverse. Okay. We can do this. We can just go into the header and duplicate this one. Come on. All right. And now let's see, expect identifier, I guess. If not expect identifier while, then return null opt. Okay, so we didn't parse anything if it doesn't start with while already. Then expect the opening parenthesis, and that's an operator. All right. Expect loop statement while opening bracket. Now statement, wait, it has to be an optional statement, of course. Condition equals expect one value. No, I think we have one. Expect expression, that's what it's called. Okay, if not condition, then throw expected condition after while statement. Let's say maybe loop condition after while statement on line something. All right. And let's say let's grab the line number of the first token. Not end token. I need to create myself some utility functions for just get the current line. So if it's not empty, then get the line number. Otherwise, just get a large number. In this case, you should probably, generate a string or something that says end of file or something. And you should probably use size max or something like that. Or size tmax, I don't remember what it was called. So you're not, 99,000 is kind of a number that someone might actually hit in a horribly huge source code. Alright, and now let's do the same thing here. If current token not end token. So the thing is, people might always enter partial source code, and you don't want your compiler to crash in that case. That's why you always have to do all these checks. Have I run out of tokens yet? Okay, so at this point, wait, actually, we need to report an error here as well. Expected what am I doing? Expected opening parenthesis after a while. Okay. Why are you unhappy? Oh, right. To string. We cannot concatenate strings and numbers. Alright. So we should be reporting these errors. And now we have a condition. And now we need to get all the commands inside the condition. So first we do expect the close bracket. After a while condition. And now we need to expect the curly bracket. All right. And at the end, we of course while commands. All right. And now here we need to do while And also again, we need to terminate here. If there is no end token. There is no token. So here we loop to actually grab all the commands. So either if the file ends surprisingly, which, makes this return false as well, that's why we have to cover it extra. Or if we finally hit the closing curly bracket. So this means, of course, if we're parsing, we will just keep reading. If the user didn't write the curly bracket, then we'll just consume the entire end of the program and then end up in the current token equals end token case. Or, in the process, we might already fail because it's invalid syntax. Who knows? But okay, and now expect statement auto current statement equals expect statement. Let's see, if we didn't get a statement for some reason, then break out of the loop as well. Because, we're skipping white space, so there's no reason we should encounter anything that doesn't generate a statement. And so now we need a list of statements somewhere. So let's see. Statement while loop. Well, let's see. What types of statements do we have? Let's say just statement while loop. All right. And do I dare abuse the parameters? I guess it would make sense. So we don't have a name. Wait, I was in the parser. Void. Why are you unhappy? Do I not have a namespace here? Oh, what is it? What are you saying? Oh, that's type, not built-in type. So it's not void that we want, it's while loop. No. Oh, it's type void void. Okay. Something like this. Yeah. So now what's next? The parameters that will just keep empty for now, and then the type, which is while loop. I should have probably looked more at the order to be able to initialize. All right. So now we have a statement variable. We will return this. While loop, okay. And now here we'll just make a heterogeneous set. So we'll do while loop dot parameters pushback condition. You're probably unhappy because it's an optional value. Okay, now you're happy. And now here where we loop to get the statements, we just append those statements. Again, value, I think. Alright. So now our parser should be ready. Let's see what this does, apart from probably spit out compiler errors. Oh, do we not yet have the operator less than in the parser? Yeah, we don't. So, whoops. Code. Wasn't there a reformat code? Okay. So let's say 5 is less than. So like assignment is always the lowest priority. Inside that assignments, and then additions or something should bind stronger. I think that's also how C does it, but I'm too lazy to look it up now, and this looks fine and, you know, easy to fix if you find out that in your language you need it. Okay. Why does it say expect comma to separate parameters? What is it doing here? Expect function definition? Oh, that might just be... What's this? Expect function call. I guess that's where we're ending up in. So is our parser. Where do we call expect function call? My guess is expect one value, expect function call. Alright, I guess let's just run this in debugger and find our way back. Okay, we're ending up here. Let's look what the debugger has here. Parse function body. Expect statement. Wait, why didn't I add the... Oh, I guess I didn't write the code yet. Alright. So, expect while loop. And then expect variable declaration. And if that doesn't work, expect expression. Well, I think it's just called loop. No, what is it called? Loop statement. Actually, let's call it expect while loop. Because, you know, in the end, really... Okay. In the end, you will have different kinds of loops, like for loops or something like that, so this is actually a better name. Expected closing parenthesis. Okay, let's just set a breakpoint here and follow this through. Okay, a while loop. We actually have it. Nice. Now we've created a while loop statement. Line number expect while. Oh, okay. We should maybe set our breakpoint here, where we actually know that it's a while. Better. Okay. It has the opening parenthesis. It updates the line number by 1. Now it expects a condition. What is the condition? It's just a variable name? I guess the less than sign is missing somewhere. Expect expression. Expect operator. Where do we have the... So we have the operator entries here. Let's see, we had to add equals somewhere else, right? Okay. No. But so something's going wrong parsing the expression already. The condition. Expect while loop. So let's set our breakpoint at the expression. And now step into it. Expect one value, that's the x. And now expect operator. It's not end token. If it's not, what is the current token? Oh, less than is an identifier. That's why it doesn't work. So I need to add it to the tokenizer. That's what's missing. Alright, where is it? Dot here. I guess just do it like this. Wait, let's just leave that running and hope that it works now. Still expecting a closing bracket. Okay, guess I should have left that. Oh, a closing curly bracket. So the condition is a less than expression, so that looks good. Expect. Oh, we're consuming the closing bracket already. So we need to say, how do we peak? Debug print, no. How did we do this in the other spots? I guess we just didn't check. Not really 100% correct. So let's see. Let's at least add a bool had closing bracket equals false. No, let's just leave that for now. Don't have that much time left. So this should hopefully parse now. Let's see what it parses into. Oh, I forgot the semicolon, I guess. So no, actually, where does it do the function body? Structure. Expect function definition. Statements. Parse function body here. Expect operator. That looks for the statement. And then for a semicolon. Okay, that's not quite perfect because it means we need a semicolon after our loop for now. But let's do it like that for now. So really the semicolon probably needs to be handled differently. But right now I need it to accept the semicolon here. It has parsed the statement. It looks... yeah. So because in C at least, you know, you don't have a semicolon. So we will get an error message now. Yeah, on line 7. And line 7. Oh, I guess that's here, really. So let's run this again, see if it's happy now. Yeah. So that's not quite how C does it, but let's ignore it for now. So you would probably have something like an intermediate function that parses a, let's call it command or something. Oh, hi Tony. I'm doing well, having a quiet day, just starting to implement loops. Alright, so while, and so you would just parse while without a semicolon, and only require a semicolon if there's a command after it. I guess not even then. And yeah, so you would just not require a semicolon after a while. Whoops. And for all other statements require a semicolon or something like that, you know. And put that wherever you loop over parsing multiple commands. All right. So we're parsing this. Let's see what it generates in the parse tree. While loop, void operator call, x less than iterations. That's nice. And here operator call x plus 1. Yeah. X equals x plus 1. And here function call print num x. So that's all exactly the stuff we expect here. So now we can go back to our parser. No, our code generator here. And handle the case of a while statement. Case, let's put it at the end. Variable name here. Case while loop. Oh, hi, empty grocery bag. You didn't read the rules. Shame on you. Be nice. Don't be rude or reactionary to people, and we'll be fine. Hello, how's it going? What were you streaming? Oh right, I don't have a bot right now. Sorry, I can't actually see what you were streaming. But hello, Raiders. I'm currently... Oh, did I... Yeah, I forgot to put... So, I'm currently implementing while loops in this programming language. We're parsing it correctly already, just not running it in any special way. You were streaming compiler development. Ooh, nice. I'll have to remember to do that. Yeah, so we have a bytecode interpreter. I guess I can probably give you a demo if I just delete the loop for now. So this is the code we can compile right now. We run the code from here. Let's see. Here, run. We pass it 3 as the only argument. And this gets parsed into well, first it gets tokenized into individual words and symbols. Then it gets parsed into a tree representing the code. And then it gets run as bytecode. And so if we run this now, just as a short summary, let's see, did it do? Yeah. So you see here, it first prints the script again, then here it prints all the individual tokens. So identifier int, identifier main, operator opening bracket, identifier int, identifier operations, closing bracket. That's basically the first line. So literals, all that stuff. Then it parses it into a tree, so it's a main function with one argument, iterators. Then it's a variable declaration x, which gets initialized to 0. Oh, I forgot, for our demo, this would have probably been nicer. X equals iterations, run it. So now we output 4 because we got 3 iterations plus 1. More interesting number. Yeah, so we have this variable declaration. Then we have x equals, so this is an equal, so it's already reformed into function-like syntax, basically. I'm not really making much sense, am I? Sorry. I was just so, like, we're at the end of this program, basically, of this, and I'm so focused on actually adding loops to this that I'm having a problem today stepping back and actually explaining that. One thing we can probably do is, yeah, go here and show you the compiled code. So these are our bytecode instructions. So we first, let's see if we can get the script on screen to go with that. All right. So first, it reserves space for the variable x, initializes it to 0. We just do that for every variable. Then we load base pointer relative -2 into it. So the base pointer on the stack points right at the start of all our variables. And before that are any parameters we got and our return value. So -2 is actually the first parameter. Then, so we push that on the stack here, and then store it base pointer relative in 0, so write it back into x. So that was basically the x equals iterations thing. Then we load x, we push x on the stack again, push 1, like the literal 1, and add them. So that's the x plus 1 here. And then we write that back to x. That's the x equals part. So yeah, then we load x again, push it on the stack, and trigger the print int instruction. So that's the print num x. So that's why you see the output here in the console. Oh, you don't see it because we haven't run it yet, but you saw like number printed :4. So that's what that was. Then we push x on the stack again. That's here. And yeah, and now we store it base pointer relative at location -3. That's where our result is. So we're returning a return value. Then we jump, well, by 1 instruction. So that's the jump from the return value to the cleanup code at the end here that the compiler generated. And all the cleanup code does is get rid of x again, pop that off the stack. And then it actually returns from the function. So we can basically parse function calls and simple stuff. And now we're working on getting a loop in there. Wait, empty grocery bag. What kind of a compiler are you doing? Are you doing like what CPU or bytecode virtual machine or whatever are you compiling to? Does the VM transpile to C, C++, or does it generate machine code? In my case, neither. This is just a struct that I did. And the bytecode VM is just, where is it? Bytecode interpret. It's just a interpreter. So it just loops over the functions, uses the opcode as an index into an array of instruction functions, and we have a function for each instruction that we support. So it's the idea of this tutorial is mainly to get people started with creating their own programming language. So I'm kind of trying to keep it fairly simple. But by making a bytecode interpreter, you learn what an interpreter is. By making a parser that generates bytecode, you kind of know how a compiler works. You know, kind of that is the idea behind this whole thing. So yeah, it's just a bytecode I made up that gets interpreted right now. But, if you know enough about assembler, you can take the knowledge of generating this bytecode to actually generate Intel machine code or whatever you want. Your language started as an LLVM front end, but you'll implement code generation for AVR assembler soon. Okay, cool. Nice. Yeah. So I have to say this language exists only for this tutorial. Whereas I have a project that I've been working on for a while where I'm actually creating my own programming language. It follows basically the same principles, but is more complex because it imitates an existing programming language and extends on it. And the existing programming language is called HyperTalk. And it has some idiosyncrasies, which, make it not a good language for teaching people how to create their own programming language. So that's why here I'm just making up my own C-like language. Yeah, but so my programming language, which I usually call Hammer, which is based on HyperTalk, is basically an English-like programming language. Sorry about that, I bumped my microphone there. Yeah, and it's kind of a scripting language, the language I work on, not this one in the demo. Alright. So I guess we can hopefully undo these changes. Yes. And that parses now. Of course, that doesn't do anything because we don't generate code for the while statement yet. So let's go into our code generator and find here is our statement for the while loop. Is this now the minimum set of features, or where are you in the picture, in the big picture? This is, we're not quite there yet. With the while loop, we are almost there. You would need conditionals, but since conditionals are implemented basically the same way as a while loop, as a loop, like you need all the same parsing techniques, I'm probably not going to do that here in the tutorial. And the one thing that is missing is calling a particular function, which I think we might do in an extra chapter. There are two problems, or two parts to that problem. One is just parsing a function call here and generating the code for that, which is pretty straightforward. It's basically the same as we did for the operators or for the print num function, just that instead of calling the print num instruction, we use the call instruction. And the second part of the problem is knowing the address of a function, so you can call it. And that can get several levels of difficult. So if you just say, I only allow calling functions defined in the current script, so in that same parser and compiler test my C file here, then it's fairly easy. Then you just have to backfill the address of the function, because the function might be defined after the function that calls it. And so you might not know the address yet. But it can get more complicated if you want to be able to combine several files. in which case you need to generate some extra table that contains the names of functions and where they are called. And then you need to, at the point where you have all the files loaded and know their memory addresses, you need to look up all the functions by name and take all the space, all the locations where they are called, and fill them in. Not sure whether I'll cover that in this tutorial or not. Haven't decided yet. Is this open source? Yes. On my GitHub, which is github.com/olywitness, there are actually several projects. So this one is called Parser and Compiler, and that references as submodules the bytecode interpreter project and the simple parser project, which are the previous tutorials I did, and this is based on. So yeah, this code is available. You can look at it. Of course, I haven't pushed today, so today's changes will take a moment to arrive after the stream. All right, let's see. We have a while loop here. So first things first, we need to remember where the loop condition starts. And that is compiled code size. And then we actually need to generate code for the loop condition, which we're currently storing in the parameters of our structure, but it works. Cool. It's way past your bedtime, so you're going to head out. Happy streaming. Thank you, and good luck with your programming language as well. I hope I'll have some time to actually visit you at some point. I think I should be... I can ban you. I can do everything but follow you. What's going on, Twitch? Okay, let's try it on the iPad. What's this? Seriously. Well, okay. Can't do that here right now. I'll have to remember to follow you though. Yeah, and thank you for leaving your people here. All right. So we're generating code for this statement. So the thing we want to do, remember, we had a loop. That's why I didn't delete that code. We have the bytecode here. And I know that was actually, don't think that was a loop. Oh no, here. So we have a loop here at the start that loads x, loads the iterations, compares if x less than the iterations, in this example 10. And then jumps over the code if that didn't work, if that is false. Otherwise, it executes the code in the loop, which again adds some numbers and then prints them, just like we're doing soon. And that's the end. No, is it? What does it do here? X plus 1. That's actually what we do. This is just other code it does. But this bytecode that we generated in the bytecode tutorial does the x plus 1, x equals x plus 1 that we have as well. And then at the end, it jumps back to the loop condition. So it goes 10 up. You see here, if it's 0, it jumps to 10. So basically, this is the code we want to generate now. So for those of you new here, that's you'd have to go back to the bytecode tutorial to see where I explained all of this in detail. But right now, that means I've reminded myself of all the function names or instruction names. So while loop. So we've generated code for our condition. So now we push a instruction jump by if 0. And now we need to remember this offset until we have written everything. So that means slice t condition false jump offset. It's probably a good thing to keep around. Jump instruction offset. Let's call it something like that. Okay, that's the jump by of 0. Now we loop over all the remaining parameters, which, if you remember, when we just wrote the parser, we looped over. We abused the parameters struct in our statement struct. We can probably show the statement. So we have this struct that is every syntax tree node. I was a bit lazy there. And so it has a name that we're using for function calls on variables, but of course not using for a while loop because that doesn't have a name in this language. Then we have a return type that we're also not using. We have the kind, which in our case says while loop. And the only other thing is we have a vector of statements, which is usually in a function call or an operator, the parameters or the operands in the case of an operator. So in this case, we say, okay, the first statement is our condition, and then our parser puts all other commands that are in the while loop and supposed to be repeated. All of those go in statements 1 through the end instead of statement 0. So that's a bit misleading, but it works. All right, so for statement in curse statement parameters. How I actually want to do parameters. Let's do a traditional loop because we want to skip the first item. We don't want to loop overall. Begin +1. And now no, statement not curse statement end ++ statement and parameters. Okay, so we're looping here over all statements except the first one. That's why it's begin +1. Looks a little more verbose, but it's simple. And now we just generate code for each of these, which we've already got our function for. All right. Why are you unhappy? Oh, right. Statement is an iterator, so we need to dereference it once. And dereference it once. Okay, so now it's happy. So now we've generated the condition and the instruction that will exit and end the loop when the condition becomes false. And now we need to generate the instruction that jumps back. So that's jump by. And then we need the relative address. So compiled code size. Is it condition offset? Again, we need to typecast it to int16 in our silly bytecode, but I've mentioned that too much now. Okay, so I'll have to think this through for a second, sorry. Basic mathematics. Not even mathematics, just calculating. So I have, for example, I'm at position 10 where my loop ends. My loop condition started at 5. So if I take condition offset 5 minus compiled code size, which is 10, then I get -5. Yeah, that means I'm jumping up 5, and that's exactly what I want. Alright, so now this does the actual looping. It jumps back to the condition, or to the code we generated for the condition, evaluates that, and then evaluates the jump instruction. This one here, jump by if false, or 0 in our case. But now we have to fill in this instruction's address to where it should jump. It should jump right after this instruction. So we go compiled code, jump instruction offset, and now parameter 2 is the jump address in our instruction, and there we just do compiled code size. So this should actually be all the magic we need. Again, this is something we've done a couple of times in this tutorial before. Remember, for the return statement, for instance, for the cleanup code, we remember a position of an instruction. We generate the instruction. We generate the instruction here and we remember it here. I was one line off. So here we generate the instruction with a 0 jump distance. And then later, once we actually know where to jump, once all of that code has been generated, sorry. Once that has been done, we actually retroactively fill in the jump address in that instruction. And the nice thing is here, we don't have multiple locations that will jump to that condition. And it's all located here. It's not like these statements will have to be able to jump to the top of the loop. And actually, I just realized, yes, they kind of will have to, but I think I can again leave that as an exercise to the reader. So, you know, most loops have a break statement or a continue statement. So, of course, a continue statement, all that does is it jumps back to the condition. So you might actually, instead of having the condition offset, well, actually the condition offset is fine, but instead of having the condition false jump instruction offset, you may actually need, again, like with the return instruction, an array, a vector of instruction offsets, of jump instructions that need to jump to the end of the array, so that every break statement can just add itself to this array. And then here at the end, instead of just filling out the 1, you loop over this array and fill in this address multiple times. Oh wait, and this is wrong? Because the jump offset is of course relative to the instruction. So we do compiled code size minus the jump instructions offset. Almost would have done that false, wrong again. Okay. Are we ready? Let's run this, parse this. And now we've generated some code. Let's first see, what have you printed? Yeah, it parses it right. That's fine. It's all in a while loop. Okay, now we're in the debugger. Let's give us some space and look at the compiled code. So let's see. Let's bring up the script again for comparison. So I remember what we're actually doing. So we're reserving space for x, that's fine. Then, and x is initialized to 0, so that means nothing more to do with the variable for initialization here. Then we load x, and we load at the address -2, place pointer relative. That, of course, is our first parameter, iterations. And then we compare them with the less than operator, yes. And that will push 0 or 1 on the stack, depending on what it is. And then here, jump by if 0. So that will jump 8 instructions. So that includes this one. So 1, 2, 3, 4, 5, 6, 7, 8. So we're jumping here. We've jumped past all these instructions. If I'm not off by one or something. So that means, yes, we jump past the end of the loop. That looks good. But if we're not jumping because it's 1, then what it does is, again, it loads x, it pushes 1, it adds the 2, so that was x plus 1, and again assigns that back to x, so that's that statement. Then we've seen this before. We load x, we do the print instruction, that's this line. And then here, that's basically the closing bracket. That says minus 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that jumps back to the start of the loop. So that looks like we've generated the correct code for this loop. And of course, if we don't, if we don't end on this statement, but actually end after it, then we do the return statement, which we've seen before, which will, set up the result, clean up our stack, remove our variables, and then return. So this all looks pretty good. So let's run this. Wait, we can just continue, I guess. Let's see what it printed. Number printed 1, 2, 3. Result 3. We've executed a loop. We only have one print statement and we executed it 3 times. So yeah, this is actually a success for today, because that's exactly what I wanted to manage, and I've only run over 10 minutes. So yeah, that's good. So that means next time we can probably deal with picking a particular function to call, which is what I mentioned before. Build a table of the first instruction of each function, and then you can just use that as the address to start executing at. And we can implement function calls, like print num, but implemented in our own language, which takes advantage of this table, because the parser then knows, okay, for this name, call this function. Yeah, and we have to retroactively be able to fill that out as well. So yeah, maybe a small aside about this function thing. These tables are things that exist in real machine code as well. For example, if you use a dynamic library, DLL or dylib, shared object, whatever your operating system calls them, or even if you just call into the system, there are something called Syscalls, which are different. Basically, Syscall is something like print num. It's kind of a built-in function that gets called through a special syscall instruction. But it's not quite like print num is only 1. It would be if I had, well, that's going too far. But anyway, so the problem is with calling functions elsewhere that both bits of code need to be loaded, and then each needs to be told where the other's function has been loaded. And that's what usually your operating system's loader does. So yeah, so that happens in your regular operating system as well. That's not specific to a bytecode interpreter virtual machine or whatever. But anyway, I'm happy that we've been able to actually execute a loop, return values. Also, don't forget, at the very start of this stream, we actually implemented reading arguments to a function. So we've done a good job today for a little over 2 hours. So now there are no, don't go on this screen, and don't load my own stream. All right. So let's see if there's someone we can raid at the end of the stream. Yeah, I guess since you people came in here and, you know, probably, what was it, half an hour ago or something when you raided. So, let's go and raid another developer who is making a space colony sim game. Some of you may know them, I don't know. Please feel free to come along. All right. If you can't stay, I understand that, but it's always nice to, one, have the numbers. You know, the person we raid gets happy as well if they see that a bunch of people come in, even if they then can't stay. And maybe, you know, you can always click follow or remember the name and maybe come back later when you have some time. So let's see what we're doing. And thank you for being here, and look on my Discord or in the schedule under this stream to find out what actually when actually the next programming stream will be, because of course the next stream on Sunday will be us playing Quern, the first-person puzzle adventure, and on Tuesday, the weekday stream starting, will first be Horizon Forbidden West. So let's see. I haven't quite decided. I might make the last stream of the week the next Friday again, another programming stream to finish this tutorial up. But I haven't quite decided yet, so keep an eye on the schedule. Okay, let's raid.